네, 그럼 시작할게요. Okay. Thanks everyone for coming again. So we will continue our discussion on Hamiltonian simulation. And today the main theme is LCU. What is LCU? It means linear combination of unitaries. And this is an important technique that was developed let's say 2012 and 2013 by a group of authors. And while this is not the state of the method right now, state-of-the-art method right now, it played an important conceptual role in thinking about Hamiltonian simulation algorithms. So we will learn about the basic ideas behind this algorithm. Okay, but just to be clear on the motivation, last time we talked about many things. We talked about quantum phase estimation, and quantum phase estimation, it basically if you have an ability to perform Hamiltonian simulation, by which I mean if you can apply e2 minus IHT, you can leverage this ability to do other tasks as well, such as energy estimation given an energy eigenstate. And also, if you begin with a superposition, which is a superposition of ground state plus some excited states, where the weight of the ground state is sufficiently large, then you can use quantum phase estimation to prepare the ground state with non-zero probability. And both of these are very useful primitives in quantum simulation algorithms. And the cost of the quantum phase estimation algorithm roughly scales as 1/epsilon, where epsilon is the desired precision. So if you want to measure the ground state energy up to a precision of epsilon, then the cost scales like 1/epsilon times something else. And that something else is essentially the Hamiltonian simulation cost for a unit time. Okay, so if you can develop a better Hamiltonian simulation algorithm, obviously that is useful in itself, but it is also useful for other purposes, such as energy estimation and ground state preparation. And that's why people are spending a lot of time thinking about how to make the Hamiltonian simulation more efficient. And formally speaking, there was this Trotter-Suzuki method, which is formally efficient, meaning that the cost scales polynomially with the number of qubits or number of fermions if you have fermions. And so this shows that all these, so Trotter-Suzuki decomposition, it shows that all these tasks can be in principle done efficiently on a quantum computer. But usually that's not the end of the story. Usually people try to make the algorithm better, faster, and using a smaller number of qubits. So so this Trotter-Suzuki decomposition, to the best of my knowledge, I'm not completely sure about this, but I believe this was first proposed by Seth Lloyd in 1996. And so for a long time, this was the de facto standard method for Hamiltonian simulation. But in the 2010s, many new ideas appeared. That's what we're going to talk about in the rest of this course. And they're interesting because they come with a better complexity bound than the Trotter-Suzuki method. So Trotter-Suzuki method, as I said, it's formally efficient, but when you account for all the costs, gate costs, you get some estimate on the total complexity, time complexity of the algorithm. And these new algorithms were interesting because at least when it comes down to the upper bound, back then, you got a better complexity bound. So that's why they were very nice. And what is very strange about these algorithms, is that many of these algorithms actually attempt to approximate this e2 minus IHT by a non-unitary operation. So it seems like a very strange thing. Quantum computers are, by definition, it's a sequence of unitary operations. So it seems like a very strange thing to like approximate this naturally unitary operator by a non-unitary operation. I guess the surprising thing is that these line of thinkings actually lead to improvements. And we will talk about the simplest of such method, known as linear combination of unitary, applied to a specific setup. By the way, if you have any questions in the middle, please ask me. You can interrupt me. Okay, so what is the basic intuition? So what we really want is the following. So we want to begin with an arbitrary quantum state. Let's call it as psi. And we want to transform this state into psi prime, which is, well, obviously we want to apply this time evolution operator. So this creating this psi prime is what we want to do. But in these non-unitary methods, what you usually end up doing is something like this. So you first somehow find the method to do this kind of transformation. So you begin with this initial state psi and another register. Here I just wrote this down as 0 just to just out of concreteness, but this could be any fixed state. So it could be a fixed state over 5 qubits or 10 qubits. The important thing is this is a fixed state, and you apply some unitary operation on psi and 0 altogether, and what you get out of that is this psi tilde prime, which is approximately equal to psi prime. Imagine they're exactly the same, but this you're in a superposition with this success case and the failure case. So so then if you measure the second register, then let's see, if we just measure the second register, then with probability P, you obtain this psi tilde prime state, and with probability 1 minus P, you obtain this failed state. We don't exactly know what this failed state is, but the important thing is that when it fails, we know that it failed. Okay, so this is so suppose somehow you can make this kind of operation, implement this kind of operation. Then the basic idea is that you somehow find a way to do this and then boost the success probability to 1. So you change P into 1 by applying a sequence of gates. So I know that this is very abstract at this point. We will actually discuss a specific example, but this is basically how these like non-unitary methods work. You begin, you somehow build this operation, and then you boost the success probability. So we'll see how that works in this lecture. But I think it's good to start with some toy example. So I like thinking in terms of qubits because they're very simple and concrete. So I'll try to do that. So I have the question. So suppose I have a 2 by 2 matrix. Let's call it as A. What I want to do is that, let's say this is 2 by 2 matrix. What I want to do is that given an arbitrary single qubit state psi, so let's say this is a 1 qubit state, I want to apply this transformation on a quantum computer. Of course, the quantum state has to be normalized properly. So what I really mean by that is that I have to divide by the normalization factor. So this is just the norm of the vector. Okay, so this is what I want to do. So how would I do that? I'll just show you how this works, and then hopefully we can discuss. Yeah, hopefully then you can ask me questions. So the first fact is this. So A can be decomposed into a linear combination of Pauli operators. So without loss of generality, we can write down A as follows. Where these are complex numbers, alpha I, alpha X, alpha Y, alpha Z, and X, Y, and Z, these are Pauli X, Y, and Z operators, okay? So that is just a fact. And so what we're gonna do is gonna be something like this. So we're gonna introduce another register. So I think in this lecture and throughout this course, I didn't really define what I mean by register. Whenever I say register, think of it as a collection of extra qubits. So register, it's just some finite dimensional quantum system. And it could be like 1 qubit, 2 qubit. It's some collection of qubits, okay? So I'll have a register consisting of 2 qubits. Okay, and with those 2 bits of information, I will encode this identity X and Y and Z. So I would, it's a 4-dimensional Hilbert space, and I will denote the basis state as I, X, Y, and Z, okay? And if you want to be super concrete, maybe you assign 0, 0 to identity, 0, 1 to X, 1, 0 to Y, and 1, 1 to Z, but of course, other choices are also valid. Okay. So what I want to do is this. So I begin, first I begin with this state. So this is a some superposition state over this 2-qubit register. And I didn't divide by the normalization factor. I'll be somewhat sloppy about this because at the end of the day, the only correct thing that you should do is to normalize the final result by the normalization factor. In any case, you begin with this initial state. And remember, we had this state psi here, right? So that's a general 1-qubit quantum state. So that 1-qubit quantum state is indeed beginning with the in the psi state. Okay, and then I'm going to apply a unitary transformation. And the unitary transformation, let's call it as U. What it does is the following. So U apply to I psi, just nothing. And U apply to X applies X. And at this point, you can almost guess what's going to happen to the other cases. Oops, but I'll just write it down. Oops, a mistake. That should be X, Y, and Z. Yeah, and this is indeed a unitary operator because, well, if you apply U twice, then X squared is identity, Y squared is identity, and Z squared is also identity. So what you see is that U squared is identity, and therefore U is indeed a unitary operator itself. The U's inverse is itself. Okay. So if we apply this U to this state, then what we end up having is this. And so far, everything is unitary. And now, we're going to do something that is a bit strange, but bear with me. We're going to actually measure, but not the entire quantum state. We're going to measure this first register. So this register that it contains information about I, X, Y, and Z, we'll measure that register in a specific basis. And we will measure that the basis is the following. So one state that I want to definitely have is the uniform superposition of all the states. And there will be other basis states, which must be orthogonal to the state, but I will not specify them because when I measure those other cases, I'll just discard that part. So I will only consider the case in which I measure this state. So if, and maybe let's call this as psi 1. So if I measure phi 1, then what you can verify is that the resulting state is actually this state up to normalization. And how that works is very simple. I mean, this is just standard Born rule, just slightly generalized. But what you just do is that you have this initial state, and you're just applying the Born rule in a slightly more general fashion. So you do this, and what you get is up to normalization, this state. Okay. So are there any questions so far? Anything unclear about this process? Okay, good. So what we can learn from this example is that at least for a arbitrary 2x2 matrix on a qubit, we can apply that matrix by applying some very specially designed unitary U, and then measuring this extra register. And I should also mention that this process is probabilistic, so this will not always work in general, but this is something that you should have expected because it's a non-unitary process. And if we can apply a arbitrary non-unitary process deterministically, then, well, okay, so I can't think of a very concrete novel argument right now, but I'm pretty sure that that will violate something that is very fundamental. So we can do this with some probability. And the thing is, this line of thinking applies quite straightforwardly to the examples that we have been discussing. So in the last lecture, we talked about Hamiltonian simulation using Trotter. And even if you have a electron, an interacting electron system, you can use transformations like Jordan-Wigner. And then you try to implement this e to the minus IH delta t. Well, we will consider the case in which delta t is not infinitesimally small, but at least if it is infinitesimally small, then you can see a lot of parallel between what we discussed in the qubit case and what we have here. So when you Taylor expand this for small delta t, well, then you will have terms like xi plus 1, y plus 1. Right, so it's probably doesn't, for a qubit, I cannot think of any useful application of this, but in more complicated cases, we will actually see applications of this. Yeah, so the short answer is there is no application as far as I can see.
Another question. You said that this is a non-unitary operations, but in example 1, everything seems to be unitary.
Oh, all right. So so there was this step. So measuring the spaces, and so if you measure this particular state, then indeed you get the right result, but you might measure other states. There is a non-zero probability for that. And when you do that, you get something different. And yeah, it's unclear what to do at that point.
Okay.
Okay. In any case, in this toy example too, now you have terms like this: xi plus 1, y plus 1. And if you expand these things, obviously you get zi plus 1, and zi plus 1 as well. I mean, their product as well. And the important thing is all of them are unitary operators. And that's because xi, yi, zi, these are unitary operators because they're the Pauli operators acting on the ith qubit. And obviously their product is also unitary operators because products of unitaries are also unitary. So in this case, what you can do is this. So let's try to write down this H in a more general form. So this P here is a product, actually a tensor product of Pauli operators. I might have called them as Pauli product operators. It's the same thing. So example, x1, x2, y1, oops, y3, 4, things like that. And you can write down the Hamiltonian in this way. And if, let's see, so what would you do now? So now to do the analogous thing, I would prepare an extra register in this state. Okay. Right. So I will have I state corresponding to this guy, and then I will have minus I delta P alpha P state corresponding to this term. Okay, and similar to the qubit example, what you want to do is that you want to apply this e to the minus IH delta t operator to an arbitrary state. So one thing that you could do is simply you have this another register which encodes this arbitrary state psi, and then what you do is this apply this unitary operation. And what does that unitary do? So given a Pauli product operator P and an arbitrary state psi, it simply applies that specific Pauli product operator. And again, this is a unitary process because if you apply this thing twice, it's an identity. So again, this U, its inverse is itself. So when you do that, what you end up doing is apply I psi minus I delta t alpha p psi. And then you would measure this first register in the uniform superposition basis. And if you measure if you measure you measure if you measure the uniform superposition state, then you succeeded. But if you didn't, then you fail. And this is not the great method, but it does the job. So the important point here that I want to emphasize again is that it is often the case that when you write down a physical Hamiltonian, like Fermi-Hubbard model, usually you can write this down as a simple linear combination of Pauli operators. And those Pauli operators, they are unitary operators. So you can design a unitary U that performs this operation. In this way, you can apply, at least so far, a infinitesimally small time evolution. And this is the basic idea behind how the Hamiltonian simulation works using this linear combination of unitary method. So I hope the name is clear at this point. A linear combination of unitary is literally a method to approximate a unitary operator by a linear combination of unitary. So obviously, if you have a general linear combination of unitary, that is not going to be a unitary operator. But the hope is that you find a linear combination which is close enough to the unitary operation that you want to actually implement. So an interesting application of this line of thinking was made concrete by these folks. So they wrote many papers of this form, but I think the simplest example from this period, which shows that you can use these methods for actual practical Hamiltonian simulation, was this paper. And what you do is something that's that may sound a bit naive. So what you do is that, let's say you have a general e to the minus IH t for some t. Then what you do is that you break this down into smaller steps where you choose to n large enough so that this thing in the exponent, this is the norm is like order 1. So it doesn't scale with the system size. And once you do that, you can Taylor expand and choose the convergence radius, and you can truncate to a finite value, a finite order. And the thing is, by doing so, you can again express this unit time time evolution as again a linear combination of unitary. So, well, this will be just identity minus NIHT minus da da da. And if you can write down the Hamiltonian as a linear combination of unitaries like that, then their linear order, quadratic order, higher order, all those things will be again linear combinations of unitaries. And if the norm of this thing is chosen to be order 1, you can, in order to get an approximation of, let's say, error of epsilon, it suffices to truncate this to an order that scales almost logarithmically with 1 over epsilon. So this way, you can try to perform the Hamiltonian simulation. It doesn't quite, I haven't told you all the details yet, but this is the basic idea. So this is a good time to stop and ask questions if you have anything. If you have any conceptual questions, this is a good time to ask.
I'm very ashamed to say that I don't really quite follow what's going on here. I mean, the scale expansion of the unitary operator, that's okay. But I guess I'm being sort of confused about where this linear LCU stuff exactly comes in this stage.
Right. So let's see. So let's say hypothetically, we have expanded that, and we can actually truncate this to a low order. So we can actually write down the expansion efficiently on a classical computer. So let's say we already did that job. So we have re-expressed this thing as a linear combination of unitary. Okay, this is the most general form.
Oh, that's what you
And
call
then
linear combination of unitaries.
Right, yes. Okay. So yeah, this P, I chose them to be Pauli operators because that's a convenient choice, but it doesn't have to be. So H is not a unitary, but H is a linear combination of unitary. So its powers are also linear combinations of unitaries.
Okay.
So all this thing, I mean, they will always be a linear combination of unitary, but the important thing is that we can truncate this to a small order. So the number of distinct unitaries that we need to consider is not too large. And that will later become important because there is this unitary here. The cost of this algorithm really depends on what's the cost of this unitary is. And as you can imagine, if you have more and more non-zero terms, its cost will grow and grow. So that's why I try to emphasize that we truncate at a low order.
So this U that shows up in the above, that's not the E of minus IHT.
Let's see, U, right. So this U is not e to the minus IH delta T. It's a different thing. So this U, what it does is the following. So let's say you have like, so far we didn't lose any generality, like any operator can be written in this form. What U does is that you have this extra register, which encodes the set of P's for which alpha P is not zero. And if the register is in the P state, then it ends up implementing this P to the target wave function that you want to simulate. Yeah, so you should think of U as like a convenient subroutine that people often use to simulate e to the minus IHT.
Okay, so yeah, now I understand the procedure, but how does that help us simulating the Hamiltonian?
Right, so I guess I haven't told you in detail how this works yet, so okay. I will talk about that, but already you can sort of see how this works because, well, let's say we have this, and then, well, we just do this. So what we do is that we prepare this state. And then we apply this unitary U. And then we measure. in the, let's see. This basis. So this is the uniform superposition state, and the other elements of the basis state, they are orthogonal to this state. And if you measure this uniform superposition state, then what you end up having is, let's see. So if you do measure this state, then what you end up having is this state. And of course, this has some caveats, obviously. So this does not always, so the probability that you measure this thing is not 1. So that's one issue. But it shows that there is some procedure from which you can actually implement this. And there is actually a better way, and we will talk about that. But the fact that this is possible in principle should be obvious from this discussion.
Yeah, okay. So then this final state that you get at the end of the measurement, is that the wave function you're looking for, or what is it? What's the meaning of this, the final?
It is, because this will be close to e to the minus this thing, because we already expanded this e to the minus IHT divided by n into this form, right? And after all this all this procedure, what we have is this operator applied to this arbitrary state psi. So that should be close to this state.
Okay. Well, okay, it's clear now. Okay, thank you.
Okay, so yeah, one extra comment that I should add here is that if you were to just apply this once and then forget, I mean, if your only goal is to apply this e to the minus IHT divided by n, such that this thing in the exponent has a like order 1 norm, then maybe this will work. But if you want to repeat this like over and over again to simulate a long time evolution, then clearly this will have some issue, because if your success probability is, let's say, half, and if you want to simulate a very long time, the probability that you'll fail at least once this way will be very large. It'll be very close to 1. So this is not a very good approach. So you need ways to fix this. And so I will tell you more about how that works, but I think it's good to talk about the main subroutines in this business, because they are used quite frequently these days, and it really plays an important role in understanding the linear combination of unitary. So there are 2 subroutines. One is called a select subroutine, and the other called as a prepare subroutine. So select, you can think of it as a lookup table, and what it does is the following. So suppose we have a set of Pauli operators, okay? So P1, P2, all the way to Pn. And what it does is the following. So I'm given register which encodes this index. So this is the index register. And I have a state psi. This is the quantum many-body quantum state that I want to simulate. And I want to apply the select operation . And what it does is that it applies the case Pauli operator. Okay, so this is what it does. And you can immediately see that this is a more perhaps a more general version of what we had before. In what we already discussed was this unitary, such that if you have UP psi, then it applies to P then applies the Pauli operator P to this arbitrary quantum state psi. The key difference between the two is that down below, we are assuming that P can be in any state. So if you have a multi-qubit system, the number of Paulis can grow very quickly. But over here, we're simply saying that we have n Paulis. So for instance, you can only have maybe 2 Pauli operators. And in that case, the select operation will only need the extra register to be a single qubit. Okay, but whatever. But either way, the main spirit of these constructions are very similar to each other. So that's a select operation. So what is a prepare operation? So prepare, you can think of in the context of the Hamiltonian simulation, these prepares the state that encodes the coefficients of the Hamiltonian. So in the previous slides, we began with states like this. So alpha P, superposition of P. And prepare does something similar. So if you apply the prepare operation to some fixed state, let's say the all 0 state, then what we end up having is this general superposition state. And of course, to put these things side by side, the select operation on this thing would be that. Okay. And these two together can be quite powerful because with this.
May I interrupt? So
Yes.
just to be clear, this K is the state of 1 qubit or can be multi-qubit state. So K
it can be multi-qubit state. So K, this is a log to n qubit state.
Oh, okay. But the coefficient alpha K, that's pretty arbitrary in this.
Right. So this can be arbitrary. Yes. So right. And this can these alphas, they depend on the context, but sometimes they encode information about the coefficients of the Hamiltonian, and sometimes they encode information about the Taylor expansion of this e to the minus IH delta t. Yeah. But they are arbitrary.
Okay. Okay.
Right. So what I'm going to do is this. Oh, by the way, so one quick comment. While it is unimportant, it is usually assumed that alpha k's are real numbers. So it doesn't have to be, but for practical purposes, this almost always does the job. Just a side comment. And I will assume that. Okay, so now what I'm going to do is that I'm going to show you how these two operations work together. So suppose we apply these operations in this sequence. So you first apply prepare, and then select, and then do prepare dagger. What does it do? So I would like to apply that to this state. the all zero state on this register, which encodes information about the Pauli that you want to apply. And then, okay, so let's just do some calculation. So we first get this state, and then now we get that. Okay, and now it's not entirely clear what the action of this prepared dagger would be. But what we're gonna do now is that we're gonna apply this all zero state bra on the left-hand side and see what happens. And that is, of course, equal to okay. So this is what we got. So physically, what this means is the following. So you begin with this state, all zero state, tensor product, the state that you're trying to simulate. And then you apply this prepare, select, and prepare dagger operation. And then you measure this extra register in the let's say, a sum basis that includes the all zero state. And if you measure all zero state, then when that happens, the state on the remainder is precisely this guy. Okay. So by using select and prepare, you can actually apply a certain linear combination of unitary to this state psi. And moreover, what this shows you is that it's the following. So you can sort of understand the cost of this algorithm by inspecting the cost of the prepare and the select. So both are very well-defined procedures, and and the cost of these methods have been actually studied very intensively. So this way we can get a more transparent understanding of the cost of this, of applying this linear combination of unitary.
So again, one clarifying question. What's the meaning of this final state, which you just underlined?
It's a post-measurement state on the remaining register. So
yeah. What does that have to do with the Hamiltonian for which we're trying to gain understanding?
Right, yeah. So suppose we have e to the minus h, sorry, this for some unit time t. And then what I would do is that I would expand this into an operator of this form, okay? And you can always do this. So let's see, did I remove something? Yeah. So what you can do is that you, given this unitary operation, you can expand that into this linear combination of unitaries. And then all you need to do is that you need to somehow find a quantum circuit called prepare, which maps the L0 state to this state, and find a quantum circuit that called select that perform this. So provided that you can find those circuits, by simply applying these three operations, you can, and measuring the zero state, you can actually implement this e to the minus IHT.
Okay, so the actual choice of the alpha k is actually governed by the exact form of the unitary operator or the exact form of the Hamiltonian that we study.
Right, right. So
Okay.
these alpha k's are related to the Hamiltonian, but to relate them, you need to do some extra work, at least if you were to use this method. Okay, so I understand that this might look very complicated because when I first looked at this, I thought it was very complicated. But so you might wonder why bother with this approach. And the reason is, in the Trotter-based Hamiltonian simulation method, there is an inevitable scaling in the inverse precision 1 over epsilon, which scales polynomially with 1 over epsilon. And it's just a fact that you cannot avoid with the Trotter-based methods. But using the LCU approach, you can actually get a sub-logarithmic scaling in 1 over epsilon. So what if the time is a constant, and if everything else is a constant, the scaling that you get is roughly log 1 over epsilon divided by log 1 over epsilon, which is essentially log 1 over epsilon. And this difference between scaling in polynomial in 1 over epsilon and logarithmically in 1 over epsilon is crucial because often for quantum chemistry applications, they tend to require higher precisions. And so this exponential improvement in the inverse precision actually makes a significant difference in practice. That's the main important advantage of the LCU method compared to the Trotter-based methods. Okay, so that's the basic summary. So in the Trotter-based Hamiltonian simulation, there is an inevitable 1 over poly 1 over epsilon scaling, but in the LCU approach, you get a better scaling. And using select and prepare, you can actually apply the desired unitary with a non-zero probability. So what I haven't told you so far is this. So I've only talked about implementing this for a unit time. And that's because this process that I told you right now, as it stands, doesn't always work deterministically. So there is a non-zero probability of failure, and we need to understand how to somehow boost that probability to 1. So that is an important ingredient. And yeah, so so today, if time permits, I do want to tell you more about how the select and prepare can be actually implemented. But I think I should first take some questions, and then if I have time, I'll talk about that.
Okay, questions from the audience?
So it seems the prepare is the only place where the Hamiltonian information is encoded. So once
yeah, okay, go ahead.
am I right?
It's not exactly correct because, but it's a good question. So maybe, yeah, so maybe it'd be good to have an example. So let's say I have two Hamiltonians. One is these are essentially the same Hamiltonians, but I think it's good to talk about how the select and prepare will look like. So in this case, the select will look like this. So let's see. And the prepare will look like this. So, and in this case, this is how the select will look like. And the prepare will be the same. So maybe one way to say this is that the select and prepare, both of them, they do depend on the Hamiltonian, but the choice of select depends on the operators that you're using. And the choice to prepare it only depends on the coefficients. And they are also related in a non-trivial way, because hypothetically, let's say I have alpha I square and there, then the prepare would be, I think, well, okay, so now this is no longer normalized, but yeah, so it'll look like this. So, and this is a very natural ordering that we used here. So each of the terms are labeled by the sites in a sequential order, but in principle, we could jump back and forth. So like if we have things in a line, we could have chosen this to be 1, 2, 3, 4, 5, 6. And you could define the select and prepare in using that convention. And that would have been also still valid. So I guess, yeah, anyway, sorry, this was a very long answer, but I think they both do depend on the Hamiltonian.
Okay, thank you.